Hey guys, welcome back. So in this box is a brand new power station made by Oukitel. This is their newest and most powerful model that they make. Powering it is a 2000 watt hour lithium iron phosphate battery bank, and it can produce 2000 continuous pure sine wave watts. Anyway, they sent me this for the purpose of making this video. So let's get it out of the box. We'll get it up on the bench, check out the features, and put it to the test. At first impressions, it's not quite as big as I thought it was going to be. And that's not a bad thing. It's fairly compact for the amount of power that it produces. And these handles on either side make it quite easy to carry around. You know, weight-wise, it's about 50 pounds, very similar to a inverter generator, a small inverter generator. So, you know, looking at this unit, they've actually organized things pretty well. On the left side, that is where you have the power inputs. It accepts AC and DC. On the front is the display, a light, the power button, and all the DC outputs. And on the right side is where you will find the AC outputs. And on the top, you've got a compartment here to hold the charging cord or any other cords that'll fit in there. Anyway, let's power this on and see what the state of charge is out of the box. And we're at 52%. Taking a look at the left-hand side, besides the charge inputs, we have couple cooling fans. So be sure to keep this area clear so the unit can cool properly. There's also a overload protection circuit breaker on the charging input. So if you have any issues charging, double check that breaker. And inside here, those are the inputs for charging. On the left, we have an 1100 watt AC input that uses a standard cord that you'd find on most computers. So if you lose this or it becomes damaged, it should be easy enough to replace. Obviously, you can charge this using grid power, but you can also use a small generator to do the same. On the right side is the Anderson connector input, up to 500 watts, between 12 and 48 volts, up to 15 amps. You can use any source of DC within that range, including your car or solar panels. For now, I'm just going to use a lab power supply and test a couple scenarios and see how this does. Before connecting up the power supply, I'm just going to double check these inputs and make sure there's no power coming out of them. They should be protected by a diode, but I just want to make sure. The multimeter is set to measure DC right now, and you can see there's nothing coming out the DC input and nothing on the AC side. Let's just double check using the AC setting. And good, there's no power coming out where there shouldn't be. So one thing worthy of note, this unit shut itself off pretty quickly after sensing no load being drawn from it. So let's turn this power supply on and see if it wakes up automatically. And it did. I see the power light just came on. I'm sure in a second that display should turn on as well. And it did. According to the power supply, we're putting in 1.7 watts at almost 11 volts, and it is showing the same on the display. So let's bump the voltage up to 12.6 volts. which is the voltage you'd see on a fully charged battery in your car. So there we're at 12.6 volts. Power supply says 102 watts, which closely agrees to the display here on the unit at 96 watts. Now this is estimating 11 hours until full charge, keeping in mind we're starting from 53%. So let's bump this up to 14.4 volts, which is the voltage your car will produce when it's running. See if that makes much of a difference. So at 14.4 volts, we're pulling 116 watts. The display here shows 110, and the estimated time to full charge is now 9 hours. I'm going to bump this up to the max this power supply can do, which is 30 volts, 10 amps. And we're pretty close. We're pulling 296 watts. The display here shows 294. And the estimated time remaining to full charge has gone down to 4 hours. Let's try the AC charging. All right, so just plugged into AC power, and I can see the input is ramping up. Should stop at about 1100 watts. We're pretty much exactly there. It's currently reading 1099 watts, between that and 1100 watts. So that is perfect. It's estimating 44 minutes to full charge. Now, I'm going to turn on the DC input as well. The manual does not say whether it supports this or not, but if it does, this should bump up by a couple hundred watts and reduce the charge time. Yep, and the input watts did jump by about 100 watts. Let's bump this up a little more to 200 watts. Yeah, and we are charging approximately 200 watts faster, and the estimated charge time remaining is now 46 minutes. So I'm going to set a timer. We'll do a time lapse and see if that is accurate. It's interesting. I thought it was still charging both on AC and DC, but it's only charging on DC. In fact, if I light the display back up, you can see the charge rate is down to 200 watts. So I'm going to let this run a bit longer just to see if this eventually shuts off. But at this point, it looks like we are most of the way there. We're at the 99-minute mark, and it's still charging at 192 watts. So the timer, it just rolled over back to 0. I'm going to keep this going until the DC charging stops, but I am going to up the voltage, see if we can't get this done a little faster. Finally, we're at 100% state of charge, and I was getting a little bit nervous. In total, it was charging for about 2 hours, just a bit less. And when looking at the time-lapse replay, I could see the AC charging shut off at about 21.5 minutes. And the rest of the time, it was just charging on DC up until now. And even though this has lithium iron phosphate batteries, which are considered very stable, they generally don't suffer from the same problem that lithium ion does when damaged or mistreated and run away thermally. But overcharging can damage them. Anyway, we're at 100% now. Let's move on and test the DC output. Guess first off, get that out of the way. And I'm going to start testing the 12-volt outputs. We have 4 in total. The bottom 2 are rated at 3 amps each. They're just standard barrel connectors. Top 2 are rated at 10 amps each. This one is a cigarette style plug that you'd find in a car. And the connector here on the right is an XT connector and a little bit more of a robust connection. Anyway, the manual doesn't make it clear whether this is 10 amps each or 10 amps total in this block. And I have seen a couple other reviews posted on YouTube that indicate it's 10 amps total that's available. So we're going to test that. I'm going to exceed the 10 amps and see if this thing keeps going. For this test, I'm going to use this cooler. It is a 12-volt cooler that runs on the cigarette lighter and should pull about 5 amps. For the XT connector, I've got these two load banks connected in parallel, and I'm going to bring these up close to the max of 10 amps. So between these two, we'll be pulling about 15 amps. This meter is wired in such a way that we can view the amount of amps going through these load banks, and this will be measuring the voltage through the barrel connector. And to turn on an output, you have to click this button here. It's just a quick click, and it's the same on the USB and the AC outputs. It's really there just to save on power consumption because each one of these has a regulator or an inverter, which does consume some power. So you don't want to have those on unless you plan on using it. So we have 13.17 volts DC out. Let's plug in the cooler at 5 amps. And the voltage output is still 13.17. And you can see we're pulling 70 watts out. I'm going to bring up the load on these load banks, keeping an eye on the amps that are pulling through it. This meter, it peaks out at about 10 amps, so I don't want to exceed it, but I'll get it pretty close. We're pulling 9.6 amps through here, about 5 amps through there. So I'm just going to let this run for a while, make sure there's no surprises. I put the brakes on the test because the load went down to 0 watts. We still had a voltage reading here, the 3.17 coming from the barrel connector, but there's no load anymore being pulled out of this cigarette style connector as well as the XT connector, despite having everything connected up. So I'm just double checking the voltage here on the connections to the load bank, see if we have any voltage. And this does not come through well, but it's 0.4 volts, which, yeah, that's nothing. So something happened. These lights here seem to indicate that everything is normal, but there is no power on those top two connectors. So let me reset it. We'll try the test again. This time we'll keep it just below 10 amps. Just turning the load bank back to 0. Let's turn this off, back on, and I hear the fridge running. We're back to 76, 75 watts on the output. At 13.17 volts, as shown on that meter, we should be able to pull 130 watts out of here before reaching the 10 amp mark. So I'm going to turn these up until we reach 130 watts. And that loud noise, it is the load bank. It is not this unit. And that should be good enough. We're at 129 watts coming out of here. So that's right at 10 amps. So I'm going to reset the timer, let this run for about an hour, and make sure things go without issue. So we just passed the 1 hour mark, and pulling 10 amps, this had no issue. So the problem earlier, it was definitely an overload, and I said there was no indicator that there was an overload, but I misspoke. If I turn this back on, you can see these icons are on solid, but before, when the overload happened, they were blinking. And according to the manual, a blinking status light means the overload protection kicked in. So the fact that the overload protection kicked in and it only shut off the top two tells me these are limited to 10 amps combined, but the bottom was still on, and these are rated at 3 amps. So most likely that is a combined number as well. So the total DC output at 12 volts seems to be limited to 13 amps. Anyway, let's move on and test the USB output. I'm going to start by double checking the output. The voltage on the USBs should be at 5 volts or maybe a little above. In this case, we're at 5.15 volts. So let's turn on a load. Now we're pulling 1.4 amps, and this is rated for 2.4. So let's bring the load up and see if it can maintain the voltage. And we are just a little past 2.4 amps. No issues with the voltage. It's staying steady. We're at 5.17 volts. Let's bring it a little higher and see if the voltage starts to buckle. Voltage is rock steady. We're at just about 3 amps, and I don't think this tester is rated to hold that for long. So I'm going to bring it back down, but I'd say that is definitely a pass. Let's try the quick charge port. This one should be rated for over 2.4 amps. So the fact that we got that on the regular port, I don't think we'll have any issues here. But the voltage is a little lower at 5.03, which is fine. We're now pulling 3 amps out without issue. Voltage is holding steady. So I would say that is definitely a pass. For this test, I'm going to max out the USB ports. I'm going to charge my oscilloscope, my borescope, my Nintendo Switch, my iPad, and these 2 laptops up here. I'm also going to plug the cooler back in to the 12-volt side just for that little bit extra push. We just passed the 1 hour mark, and a couple things finished charging, like the borescope and the Chromebook. Everything else is still charging, so I'm just going to let it run a little bit longer. We just passed the 99-minute mark. Both laptops, they are fully charged, as well as the borescope, and everything else is getting pretty close, above 80 or 90%. So I want to move on to the AC side of things, but before I do, I haven't covered this light yet. To turn it on, it's just a long press. And as you can see, it's quite bright. A short press to cycle through the different settings. And to shut it off at any time, you can do a long press or just a short press through all the modes, and that'll shut it off. Anyway, I'm going to get all the stuff disconnected, turn it around, and we'll test the AC output. And similar to the other side, we have 2 cooling fans, so be sure to keep those clear. We have a switch to turn the inverter module on and off. And under this door right here, we have 6 outlets. And it looks like it's the 15 amp plug, and it will also accept a 20 amp plug as well. Let's start easy. We've got the oscilloscope connected so we can visually see the sine wave output from this inverter. Also, the kilowatt is connected, and running through it's a space heater. So let's power up the inverter and take a look at the sine wave. And you can see it's very clean. The scope says 114 volts, 60 hertz. The kilowatt, though, it disagrees a little bit. It says 109.6 volts. Exactly 60 hertz. So the voltage, it's a little low. The standard here is 120 volts, plus or minus 5%. So the utility providing power to your house can deliver between 114 and 126 volts. And yeah, 109.6, it's a little out of range. I'd like to see it higher, but I don't think it's going to hurt anything given that we're right at 60 hertz. So let's apply a 750 watt load. You can see the hertz are still dead on at 60. We're pulling 625 watts. The meter here closely agrees at 615 watts. Estimated runtime is 2 hours at this load, and the sine wave still looks good. Let's double that to 1500 watts. We're still at 60 hertz. 1,235 watts, and this closely agrees at 1,224, and it's estimating 50 minutes of runtime at this load. Now, this should be pulling 1,500 watts, but because the voltage is down, the total power being pulled is also down as well. But you can see sine wave still looks good. And everything is pretty much where it was without a load. So I would say this is a pass. According to the manual, you can make some adjustments. You can switch this from 60 hertz to 50, or you can switch the output from 110 down to 100. There's nothing documented on how to bring it up to 120, but let's try those adjustments and see if they work. To adjust the hertz, it's just a long press on the inverter button, then a short press to switch it to 50 hertz. And now it's locked in. Let's turn the inverter on. And you can see we're at 110 volts, 50 hertz. So let's try bringing the voltage down to 100 volts. And to do that, it's 10 short clicks. And now it's switched to 100, 220, which this does not have 220 output. So let's turn it on. And you can see we're at 101 volts, 50 hertz. Let's try 100 volts at 60 hertz. All right, 60 hertz is locked in. We're at 100 volts, 60 hertz. Not bad. This power station supports UPS mode, which basically means when you're connected to the grid, it's charging and maintaining those batteries, and at the same time, you can use all of the outputs. And when the power fails from the grid, it'll transition within 10 milliseconds over to the battery bank. So that's what I'm going to test out. going to start by just turning on the grid power to start the charging process. Grid power is on. You can see it's charging. The power from the grid started at 120 volts, and it's dropping as the current is increasing, charging those batteries. So while that's ramping up, I'm going to turn on all these outputs. And we've peaked out at 1100 watts. The kilowatt says we're at 1196 watts on the input. And if you look at the voltage, the grid power did drop. We're at 114 volts. And on the output, we're at 113.8. So the grid power, it is going straight through the unit. If we were running on the inverter, the output voltage would be lower, closer to the 109 volts that we saw earlier. Anyway, for this test, I am going to load it up with a 750 watt space heater. And what I want to see here, especially when on grid power, is what the wattage is that we're pulling. Because right now we're pulling close to 1200 watts. And this is a 15 amp circuit, so it's limited to 1800 watts. What I want to see is that the charge controller compensates and sees the 1800 watts, and it reduces the amount of current going to those batteries and brings things down closer to where they are now. Now, I've also got this battery charger here. It is all digital. And what I'm going to do with this is kind of monitor the switchover. That 10 milliseconds, it could cause an interruption. And something like this, where there's no analog switch, it's all digitally controlled, is sensitive to something like that. So that is charging now. Let's turn on the load and see what happens on the watts. And it peaked at 1700 watts, but it is dropping. So the charge controller is compensating. It's reducing the charge going to those batteries. And you can see the estimated time to full charge, it's increasing. Let's turn off the grid power and see that things transition. No issues there. You can see the output voltage, it dropped to 109 volts. So we are on the battery bank and there's nothing coming in, and this battery is still charging just fine. So let's switch back to grid power. Yep, things look perfectly normal. So I would say that is a pass. And one thing to keep in mind, the manual does say when running in UPS mode, do not exceed 1100 watts on the output. Anyway, I'm going to let this fully charge. I want to get it to 100%. And once it's there, I want to test the capacity. This is advertised as a 2000 watt hour battery bank. So I want to run it from 100% down to 0 and see if I can get 2000 watt hours out. Actually, before testing the capacity of the battery bank, I want to do another load test and just push it right to the limit of the 2000 continuous watts. So I'm going to put one space heater on high, the other one on medium, and that'll get us pretty close to the 2000 watts. And then I'm going to use this fan that I have connected to get us right up to the edge. And assuming things run fine, I'll bump it up and exceed the max running watts and see how long it'll keep going. All right, the first space heater, it's on high. We're pulling 1,143 watts. Let's turn the second one on the low setting. And we're now pulling pretty close to 1,800 watts. It's at 1,768. I'm going to turn the fan on low. The fan has a bit of a surge with it, but it handled it fine. We're pulling just about 1,900 watts. So I'm going to let it run like that for a bit. Make sure things run without issue. We just passed the 10-minute mark and no issues. We're pulling just under 1900 watts, 35 minutes remaining, and according to the scope, we're at 112 volts, exactly 60 hertz. So I'm going to turn off that large fan and bump this space heater up to high, which will exceed the continuous rating, and let's see how long it'll run for. So we're now pulling 2,363 watts. And you can see there is more noise now on the sine wave. Still at 112 volts, exactly 60 hertz. And that's it. The inverter just shut down. It's indicating it's overloaded. It ran for about 2 minutes in that condition. So overall, not too bad. It's also worth noting the cooling fans. They are running, but I can barely hear them. And that's pretty good, considering we were running close to max load for 10 minutes and then beyond the max for an additional 2. The power station, it is charged to 100%. I used the AC charger to do it. Now this has a 2000 watt hour battery, and that is the rating based on pulling the load directly from that battery bank. But when it goes through the inverter module, some power is lost due to inefficiency. So ideally, I would get around 90% efficiency, meaning 1800 watt hours out to that space heater of the 2000 in that battery bank. But I am kind of doubting that I'm going to see that based on the earlier testing, because after the AC charging was done, the DC kept going for about an hour and put about another 200 watt hours into it. So I think we're going to see somewhere around 1.6 kilowatts. So let's start the test, and I'll use the kilowatt to track the total kilowatts used and see how we do. I pulled 1.58 kilowatts out of this unit for about 78% efficiency. So I'm going to recharge this using the AC cord and then top it off with the DC and try this again. Let's try this again. This time it's been topped off with the DC charger. We'll see if it lasts any longer. Pretty consistent to the first test. About a minute less. The efficiency is about the same though, at 77.5%. Pretty much everything I've tested so far has been a resistive load, but this is capable of a 4,000 watt surge. So I'm going to try some inductive loads and see how well it handles the surge. Try a drill. An angle grinder. How about a small refrigerator? No problem. Let's try 2 small refrigerators. The total runtime, it's estimating at 12 hours for these two little refrigerators. And that's assuming that these are on constantly, which they're not. So let's add one more to the mix. This deep freezer, it is currently unplugged. So let's plug it in and see how it handles it. It surged up to 800 watts, and now it's settled down to 243. Freezer is running normally, and so are these small refrigerators. So there's no issues here. It handles it without issue. The estimated runtime, it has now gone down to about 6 hours, pulling the 232 watts to keep these three running. So let's try something bigger. Let's try a 13 amp shop vac. A microwave for 5 minutes. Pretty impressive. My first generator was a 3,250 watt generator, and it could not start a microwave. This is a 2 horsepower air compressor. It needs 1,100 watts continuous to run, but to start it, it needs over 3,000 watts. If anything's going to cause this to buckle, it'll be this. The inverter, it overloaded, couldn't start the compressor. And to be fair, that's a hard compressor to start. It requires quite a surge. In a real life situation, if you run this down to 0, the assumption is you don't have grid power and can't use that to charge it. So I know we tested the DC charging with the lab power supply, but that was limited to 10 amps. Potentially it's better with the car. So let's plug in the DC charging. And right now the car is off. And the charging is ramping up. Looks like it's stabilized at about 26 watts. So that's going to take a while to charge this unit. And we're starting at 87%. It's estimating about 16, 17 hours. Let's start the car, see if the charge picks up. Yeah, and it did pick up. We're at about 104 watts. And the estimated time to full charge is 3 hours, starting at 87%. So yeah, I wouldn't say this is the most practical option, but there are things you can do to speed this up. You can get a DC to DC converter to bump the 12 volts from your car up to 48 volts, 15 amps, for a total of up to 500 watts, and that'll accelerate this quite a bit. You could also use an inverter, but in my case that's not really an option because I need 1,100 watts to charge this with AC. My car's alternator, it's limited to about 1,300 watts. So if I use an inverter powered from my car, it doesn't leave much to keep the car going. Anyway, let's try a small inverter generator and see if it can charge this unit. Overall, this power station made by Oukitel did a great job. It handled just about everything that I threw at it. And I think for most people, this would do the job. Not everyone has a yard. A lot of people live in the city or an apartment, and a generator just isn't an option. And even if it is, maybe they're not comfortable starting and maintaining small engines, or maybe physically it's hard to do. And there's no maintenance. It'll get you through a majority of the power outages. Anyway, I wanted to thank Oukitel for giving me a chance to review this unit. They sent this to me for free, but I'm not getting paid to make this video, and I'm not making commissions on the sales of these units. But if you're interested in finding more information, I will leave that down in the description. So I hope this video helps someone. Thanks for watching.